Okay, so today we started going over acids and bases, and I want us to make sure that when we think about acids, we think about a lemon juice, and when we think about bases, we're going to think about soap. So how do they feel? Okay, so lemon juice, how does it taste? It tastes sour, and soap is bitter. How do they feel? Lemon juice is going to, if we take away the sugar, it's going to feel like water. Whereas a soap is going to be slippery. Reaction with metal. Remember, we're going back to single replacement reactions. It produces hydrogen gas. We got to see the hydrogen gas actually pop when I put the flame in there. Bases do not react with active metals. Both have high electrical conductivity. Reaction to litmus paper. Remember, litmus paper tells the difference between acid and base. They're blue or red. So an acid is going to turn blue litmus paper, turns it red. And bases turn red litmus paper blue. Bubba. Bases are bubba blue. When added to phenolphthalein, remember that was the indicator that we used in class. We saw it colorless or translucent. And for a base, it was pink. Reactions with fats and oils, it does not react as an acid. However, that's why we use soap, because they do react. Corrosive, which means eat away. We learned that at the beginning of school. And both of these guys are highly corrosive, depending on the concentration. We haven't learned concentration, but we will soon. Litmus paper and phenolphthalein are examples of indicators, which are substances that change color. Whoops. These guys change color in the presence of acids or bases. Okay, I used the cabbage juice indicator in class. Remember, I boiled that cabbage and we got to see the different colors. Okay, so our TEK tells us to define the differences distinguish between Arrehnius and Bronsted Lowry. So let's look at the Arrehnius. We're going to pronounce that Arrehnius. Arrehnius. So this definition focuses on ions that are produced when the compound is dissociated in water. And remember, dissociated means to break into its ions. So break into ions. Acids ionize to produce a hydrogen ion, an H+1, because when it gets rid of that, when it transfers that electron to the anion, we're just left with one proton, and we call it a proton. Hardest part of chemistry here is being silly. Mono means one. Protic means proton. So we have one proton. So our Arrhenius acids ionize to produce hydrogen ions when there's just one hydrogen ion. We call it monoprotic. So, So an example is hydrochloric acid. Diprotic, 2 protons, so this one's going to produce 2 hydrogen ions, and an example will be sulfuric acid. Goodness, this lead is just breaking. Triprotic, 3, it's going to produce 3 hydrogen ions. An example will be phosphoric acid. Now, to go back to remembering how to name acids, if the hydrogen is with an element, we're going to add hydro. Goodness gracious. We add hydro to the element and change the ending to ic. So we have the prefix hydro and the suffix ic. If the hydrogen is with a polyatomic ion, do not add the prefix hydro. We're going to name the polyatomic ion, change it from H to ic, and ite to OUS. So we are going to underline Br. That's just the element. So that tells me that we need the prefix hydro. So we'll have hydrobromic acid. SO4, that's a polyatomic ion. So we don't use the prefix hydro. So this will be sulfuric acid. HNO2, this is nitric. So this will nitrite. So we'll have nitrous acid. Nitrite, ITE, becomes OUS. H2SE will be hydroselenic acid. BO3, this is borate. 8 becomes ic, so we have boric acid. Now, writing formulas, we're going to do the opposite. So we have the prefix hydro. That tells me that this is just an element. H plus 1, Cl minus 1, swap and drop, and we have HCl. Ic becomes 8, so this is nitrate. H plus 1 and O3. OUS is ITE. Now, we have to be careful with this because it does say sulfurite. That's not correct, but we do know that we have sulfite. So that's H plus 1, SO3 minus 2, swap and drop, and we have H2SO3. Phosphorus will be ITE, so that'll be H3PO3. So that's an Arrhenius acid. An Arrhenius base ionizes to produce hydroxide ions. Examples of the hydroxide ions are going to be sodium hydroxide or magnesium hydroxide, any of those. So that's Arrhenius acid. It's based on the ions produced. Now we have the Bronsted-Lowry definition. The Bronsted-Lowry defines an acid as a proton donor. Okay, so sorry about that. Defines an acid as a proton donor. So we're going to draw our arrow. Always when we write an acid for Bronsted-Lowry, we're going to draw an arrow going away because it's going to donate a proton. Bronsted-Lowry base is a proton acceptor. It receives it. So we're going to draw our arrow towards it. All Arrhenius acids and bases would be classified as Bronsted, we should capitalize that, Bronsted-Lowry acids and bases. Okay, so looking here, we have our conjugate acid base pair, or Bronsted-Lowry. A conjugate acid base pair are two substances related by the loss or gain of a proton. Acids make conjugate bases, and bases make conjugate acids. I should not have put this in brackets because that says concentration. I should put this just in parentheses. Sorry. Okay, so looking here, we have reactants to products. So I asked, what happened to my reactant to make it look like a product? And you can see that it gains a hydrogen. So if we accept a hydrogen, it's going to be a base. And we just said bases make conjugate acid, so this would be my conjugate acid. What happened to water to make it look like a hydroxide? It donates a hydrogen, so this is my acid, and this would be my conjugate bases. The acids and bases are on the reactant side, and the conjugate acid or conjugate base is on the product side. And remember that these do go back and forth until an equilibrium is established. The conjugate base is the formula after an acid has donated a hydrogen. The conjugate acid is the base after it has accepted a hydrogen or a proton. So complete the following. What happens if we're an acid? Remember, we're going to donate a hydrogen. So this one will be H. We're going to subtract 1. So this will be C2O4. And since we lost the plus, we now have a minus 1. Acid again. We're going to donate that hydrogen. So we'll have BO3 minus 3 this time because we minus 2. And then we gained a negative because we lost a positive. So it's negative 3. A base. Remember, a base accepts or receives that proton. So ammonia, NH3, will become NH4 plus 1. Here, again, we're going to accept that hydrogen, so it becomes H2SO4. No more minus 1, because minus 1 plus 1, it becomes neutral. A substance that can act as both a Bronsted-Lowry acid or base is called amphoteric. Amph, both. This means it can donate or accept an electron. A proton. Oh, geez. Water is an example. If water acts as an acid, so remember acid donates, the resulting conjugate base would be OH minus 1. If the water acts as a base, meaning it receives, the resulting conjugate acid would be H3O plus, and this is called a hydronium ion. And we're going to go into that when we talk about pH. So a substance that is able to donate more than one product is called polyprotic. So it's a substance able to donate more than one proton. Last but not least, strength versus concentration. We measure concentration in molarity. Remember, molarity equals moles divided by liters. Yes, we're going to learn about molality. Kilograms of solvent instead of liters, normal, and I believe that's all right now in PreAP chemistry. The strength of an acid or a base is based on the percent ionization or dissociation. We've learned that word several times. Remember, it means to break into ions. Acids and bases that ionize or dissociate nearly 100% are considered to be strong. You must memorize the strong acids and the strong bases. The strong acids, we began last unit, the strong acids are hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, and chloric acid. 1, 2, 3, 4, 5, 6, 7. Strong bases are all of your alkali metal and alkaline earth metals plus hydroxide. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, magnesium hydroxide, strontium hydroxide, and barium hydroxide. Okay. So if an acid or base is not on the list above, then it is not considered strong. It is considered to be weak, which means it does not break into its ions, does not dissociate at nearly 100%. Okay. So let's recall a strong electrolyte are strong acids or strong bases, and a weak electrolyte are weak acids or weak bases. The concentration of an acid or a base is determined by molarity. Generally accepted standards, a concentrated will be about greater than 5 molar, and dilute is going to be less than 4 molar. So let's practice on this. Go ahead and pause this video so you can practice, and then we'll go back to it and then come back to it. So hydrochloric, this is going to be strong. Since it's strong, it's going to be a strong electrolyte, but it's only 0.5 molar, so it is a weak, I'm sorry, not weak, it's diluted concentration. So concentration is going to be concentrated or dilute. This is strong or weak. Strong or weak. Sodium hydroxide. Sodium hydroxide is one of the alkali metals plus hydroxide, so it is strong. That means it's a strong electrolyte, and it's 8 molar, so it's concentrated. Ammonium hydroxide, this is going to be weak, so therefore it's a weak electrolyte, and it is dilute. Chloric acid is strong, so it's a strong electrolyte, and it's only 2.5 molar, so it is dilute. Acetic acid is not one of the ones we had to memorize, so it is a weak acid and weak electrolyte, but it's 12 molar, so it is very concentrated. 18 molar nitric acid, this is going to be a strong acid, so it's a strong electrolyte, and it's 18 molar, so it is very concentrated.